So let's start. Welcome everyone. This is the seventh tutorial session in the subject Mechanics of Solids. I am Sukanya Karmakar, a fourth year PhD student in the Department of Civil Engineering at IIT Kanpur. Today we'll be dealing with concepts which was covered in the week 7 of the course Mechanics of Solids and focusing on mainly the constitutive relationship between stress and strain, how the relationship was basically the relationship was established, and and using the concept of constitutive relationship. So let's start the problem solving session. Okay, the first question reads that an elastic material with modulus of elasticity E and Poisson's ratio nu originally fills a square cavity of sides 2a and length L in rigid block. A rigid uh, just hang on for a second. A rigid cap is placed on the top of the elastic material. Okay, uh, and there is a force F naught acting on the cap. The height of the elastic material is found to be decreased by an amount C. We have to calculate the magnitude of the force F. Okay, I'll draw the diagram. This is so you have a block like this, and on top of this, you have a block. The sides of these blocks are 2A and 2A, and you have a force F naught acting on the top. And if I look at the cross section of this block, see, let's say if I you cut the block with a plane like this. Sorry. Suppose this is a cutting plane moving like through this block. This is the and the after cutting the cross section of the block is what I'll draw now. It is this is the bigger block, and here within this you have a cavity sort of thing, and on top of like within the bigger block there is a cavity, and over this you have the smaller block on which the force F0 is acting. The side lengths, the total side length is 2a, and the force F naught is acting symmetrically so that the remaining two lengths are A and A. This length is L. Since you have a force F naught acting from equilibrium, there will be F naught reaction from the floor. The material which is present inside this you have some material. Its Young's modulus is E, Poisson's ratio is nu. And you have found that the block moves inside by an amount C. You have to calculate the magnitude of force F naught. So there is an elastic material with modulus of elasticity E and Poisson's ratio nu. Originally fills there is a square cavity of side 2a and height L in a rigid block. A rigid cap is placed on top of the elastic material. A rigid cap is placed on the elastic material, and there is a force F naught acting on the cap, and there is a force F naught acting on the cap. It is seen that the height of the elastic material, the height of the elastic material to have decreased by an amount h, to have decreased by an amount C, sorry, by, decreased, basically the material is getting compressed, that elastic material. You have to calculate the magnitude of the force F naught. Calculate the magnitude of force F naught. So, as we can see in this cross section, let's consider this direction to be Y, this direction to be X. So the block is free to move in the Y direction. Like it's like the I should not call it the block. Like this material which is present in the cavity, it can deform in the Y direction. But there is no deformation in the x or in the z direction. Let's say z is this direction, because it is enclosed within the cavity in the x direction, and z direction is when the figure is extending out of this plane, right? That is the z direction, and in the x direction the elastic material is constrained, so the strains in those directions are zero, but there is a strain in the deformation is possible in the y direction, so there can be a strain in the y direction. So let's use the stress strain relationship, and let's write down the strain relationship. So the the block is allowed to deform in y direction, that is in the y direction epsilon y can have a value delta, but epsilon x and epsilon z is equal to 0. Okay. Now we know from the stress strain relationship, from stress strain from the stress strain relationship, we know that epsilon x is, if I take 1 by E common, sigma x minus nu times sigma y plus sigma z. Epsilon y is equal to 1 by E sigma y minus nu times sigma x plus sigma z, and epsilon z is equal to 1 by E sigma z minus nu times sigma x plus sigma y. Now this is equal to 0. This, let's say, has a certain quantity delta, and this is again equal to 0. Now we can simplify these, right? Let's take this to be equation 1, this to be equation 2, and this to be equation 3. So uh, equation, let's simplify equation. Let's equate equation 1 and 3, like, right? So Okay, we can write that sigma x minus nu times sigma y minus nu times sigma z. This is from equation 1. And from equation 3, sigma z minus nu times sigma x minus nu times sigma y. This nu times sigma y is there on both the sides. So sigma collect sigma term sigma x on one side. This becomes 1 plus nu, and sigma z on this side. So this is also 1 plus nu. So we can write that sigma x is equal to sigma z. This is equation number 1. Now substitute this in equation number 3. So using using equation 2, and here I have used, just hang on for a second. Sorry. Okay, so we used equation 1 and 3 and developed this relationship. Let's name this 4, and this was using 1 and 3. Now using 2, we have sigma y plus nu times sigma x, and sigma z is equal. So write it to sigma x. We can write it to sigma x is equal to 0. So we have a relationship between sigma x, sigma y, and sigma z, right? Sorry, I should have written sigma y plus nu times, this is sigma x and sigma y, so 2 sigma x, and this is equal to some quantity delta, and I have a 1 by e term here. So sigma x, what can we write as sigma x? First it should be delta by e. Okay, then I should write, sorry, I'll get a minus sign here, plus sigma y, right? Then I will get 1 by 2 nu term here. So if I open the bracket, it will be sigma y by 2 nu minus delta by 2 nu e. Sorry, doing all wrong maths today. I don't know what is wrong. So sigma y by 2 nu sigma x is equal to e delta. So sigma x will be sigma y minus e delta divided by 2 nu. Okay, this is, let's say, equation number 5. Now so we have a relationship between sigma x, sigma y, and sigma x is equal to sigma z. So now we will be using equation, let's say, we'll be using equation 5, using equation 5 and let's say use equation 3 and 4. Basically, I want to solve, like, develop an expression for, let's say, sigma y in terms of the material properties, right? So here we have sigma z is nu times sigma x plus sigma y is equal to 0. This is equation number 3. Here, now sigma z is equal to sigma x. So sigma x minus nu times sigma x minus nu times sigma y is equal to 0. So I can write nu times sigma y is equal to sigma x into 1 minus nu. Now for sigma x, I can substitute equation number 5. So nu times sigma y is equal to, using equation 5, sigma y by 2 by nu, sigma y divided by 2 nu minus E delta by 2 nu. This multiplied by 1 minus nu. Now from here you can solve for sigma y, right? So sigma y is nu minus 1 minus nu by 2 nu. And on this side I have 1 minus nu by, this is 2 to be clear, 2 nu, and multiplied by E delta. So from here, if we solve for sigma y, I'll give you the simplified expression. It will be 1 minus nu by 1 plus nu, 1 minus 2 nu into E delta. So sigma y is nothing but, you have the force A acting on a square cross-sectional area where the sides are 2a and 2a. So the area is 4a square. So sigma y is nothing but the force, that is F naught, divided by 2a into 2a, that is 4a square. So sigma y is F naught divided by the area, which is F naught by 4a square. And delta is nothing but, the strain is nothing but the change in length, that is C, the amount by which there is a compression, divided by total length, that is L. So this is C by L. So if we, in this expression, if we substitute these two expressions, F naught by 4a square is equal to 1 minus nu by 1 plus nu, 1 minus 2 nu E C by L. So from here you can write F naught is equal to 1 minus nu, 1 plus nu, 1 minus 2 nu, 4a square EC by L. So we had to calculate the magnitude of force F naught. So for this condition, the magnitude of force F naught should be of this form, right? This is the, you can say, mm, like, given the conditions given in the question, this is the magnitude of F naught. So any doubt in this question? Okay, let's move on to the next question. Okay. Thank you for responding. So we'll move on to the next question. The stresses in a flat steel plate, which is under a condition of plane stress, is mentioned. So you have to find out a number of quantities in this question. The stresses in a flat steel plate in a condition of plane stress are sigma x is equal to 130 MPa, sigma y is equal to minus 70 MPa, tau xy is equal to 80 MPa. Since it is a plane stress condition, sigma z is 0. Still, I'll write sigma z is equal to 0. Nu is equal to zero point 0.3 and E is equal to 205 GPa. You have to find the strain in x direction, the strain in y direction, the strain in z direction. You have to find the shear strain, the major principal strain, and the minor principal strain. Major principal strain and the minor principal strain. And the stress state has been given to you. So the stress state which is given to you is, let's draw the x-axis in this direction and y in this direction. So this is sigma x, this is sigma y, then you have this is tau xy. So first you can um locate the value of the principal stresses. So how we will calculate the principal stress? You can use the equation of like the concept of Mohr circle basically. Sigma 1 comma 2, the major and minor principal stress. It is sigma x plus sigma y by 2 plus minus the radius, which is sigma x minus sigma y by 2 whole square plus tau xy whole square. Just plug in the numbers and you find out the major and minor principal stress. Sigma x is, this is 130 MPa, This is minus 70 MPa and this is 80 MPa. So this minus 70 by 2 plus minus, this will be 130 plus 70 by 2 whole square plus 80 whole square. Like when you solve it, I'll just give you the numbers. It will be, this will be 30 straightforward, and this is 128.06. So sigma 1, which is the major principal stress, is 158.06 MPa, and the minor principal stress sigma 2 is minus 98.06 MPa. Now, first let's calculate epsilon x, that is the strain in x direction. We know that strain in x direction will be sigma x by E, and because of the Poisson's ratio, minus nu sigma y by E minus nu sigma z by E. Fine. So we can take 1 by E common and write this as sigma x minus nu sigma y minus nu sigma z. Now sigma z is 0. So this is 1 by, what is E? Here we'll do the calculations in MPa. So this is 205 into 10 to the power 3 MPa. So let's substitute that here. 205 into 10 to the power 3. Sigma x is 130 MPa and Poisson's ratio is 0.3 into sigma y is again minus 70. So this is minus 70 MPa. If you will calculate this, you will get 736 into 10 to the power minus 6. Now strain is a dimensionless number, so no unit. Similarly, you can calculate epsilon y, which will be sigma y by E minus nu sigma x by E minus nu sigma z by E. Now sigma z is 0. So 1 by E sigma y minus nu sigma x. Substitute the value of E, which is 205 into 10 to the power 3 MPa. Sigma y is minus 70, minus nu is 0.3, and sigma x is 130. So if you'll solve this, just hang for a second. Am I still connected? Okay, just hang on for a second. Okay, there is a small technical issue. Just hang on for a second. Okay, am I audible? Can you please confirm whether I'm audible? Okay, okay, thank you. So if we'll solve this number, you'll get minus 531 into 10 to the power minus 6. So you just calculated epsilon x and epsilon y. Now what will be epsilon z? Epsilon z will be sigma z by E minus nu times sigma x by V minus nu times sigma y by E. Now epsilon z is 0 because this is a plane stress problem. So what you are left with is minus nu by E sigma x plus sigma y. So this is minus zero point 0.3. E is 205 into 10 to the power 3 MPa. Sigma x is 130 and sigma y is minus 70. So if you'll solve this, you will get minus 87 into 10 to the power minus 6. No unit because it's train. So sigma z is done. Then you need to find the shear strain. Now we know that E is equal to 2g times 1 plus nu. So what we can calculate G is equal to E by 2 times 1 plus nu. Now E is 205 into 10 to the power 3 by 2 1 plus zero point 0.3. This you will get to be 78.84 GPa. Now, shear stress, that is tau xy, is equal to G times gamma xy, or shear strain gamma xy is equal to shear stress tau xy divided by G. Now, what is shear stress? 80. It's given in the question that shear stress is 80. 80 divided by G, which is 78.84. And if you solve this, you will get this into 10 to the power 3 because shear stress is 80 MPa. Don't have this number with me. You can solve this and get the value of shear strain. Now, once shear strain is done, in this question, was there any point of calculating the principal stresses? I don't think so. There is any point of calculating the major and minor principal stress. Okay. Then you have to find the major principal strain and the minor principal strain. Now you know epsilon x, epsilon y, epsilon z, and gamma xy. So you can like like you'll be using epsilon x, epsilon y, and gamma xy to calculate the principal strains in the to calculate the principal strains. So so epsilon 1 and it will be epsilon 2, the major principal strain and minor principal strain will be epsilon x plus epsilon y by 2 plus minus epsilon x minus epsilon y by 2. The only change in the formula is gamma xy by 2 whole square. Like if you compare the equation of print this stress, more circle of stress and more circle of strain. In place of sigma x, you have epsilon x. In place of sigma y, you have epsilon y. But in place of tau xy, you have gamma xy by 2, which is a manifestation of the which manifests these two manifests in the derivation itself. Now epsilon x is 736 into 10 to the power minus 6. So 736 into 10 to the power minus 6. Epsilon y is minus 531 into 10 to the power minus 6, minus 531 into 10 to the power minus 6 whole divided by 2 plus minus under root of 736 minus plus 531 divided by 2 whole square. I've taken 10 to the power uh, minus 6 common. Let's calculate this number. This number, I want the value of gamma xy. It is 1015 into 10 to the power minus 6. So if I use this number here, 1015 by 2 whole square, gamma xy by 2. So when you solve this, you will get epsilon 1 to be 914.21 into 10 to the power minus 6, epsilon 2 to be equal to 709.21 into 10 to the power minus 6. So in this question, you were given an element which is under plane strain. That is, you had sigma and in the, let's say, in the xy plane. So you had sigma x, sigma y, and tau xy. Sigma z was 0. Because of this plane strain, you will have you will have strain in x, y, as well as in the z direction. Why did you have the strain in z direction? Because of the Poisson's ratio effect, like even like because of these terms of minus nu x minus nu sigma x by e, basically because of the Poisson's ratio effect, you had strain in z direction. Then, using this constitutive relationship, you could calculate. Yeah, earlier also you used constitutive relationship only. You found out the strain in the xy plane. Now, since you know the strain in x direction, y direction, and gamma xy, that is the shear strain, you could locate the major principal strain and minor principal strain. Okay. Okay. This question is understood. Like it's done. So, any doubts in this question? Okay. So, if there are any doubts, we can always take them up at the end of the class. So, moving on to the third question. So, it is the question reads like this. It is proposed to check the safety of a thin-walled cylindrical pressure vessel made of hot rolled low carbon steel by measuring changes in length and circumference as the internal pressure is increased. How much change in length would occur if the material yielded? The material yields at 250 MPa, and we have to use the maximum shear stress criteria, that is the Tresca criteria, and the relationships for the thin wall pressure vessel. Uh, we'll have to use them. That is, sigma theta is equal to PR by T, sigma Z is equal to sigma theta by 2, and sigma R is equal to 0. And there is another part of the question. How much change in circumference would occur if the material would yield? So let me write down this question. It is proposed to check the safety of a thin walled cylindrical pressure vessel made of hot rolled low carbon steel by by measuring changes in length and circumference as the internal pressure is increased. The material yields at 250 MPa. We have to use the maximum shear stress criteria and the relationship sigma theta is equal to PR by T, sigma Z is equal to sigma theta by 2, and sigma R is equal to 0. We have to find out how much change in length, how much change in length would occur if the material yielded, how much change in circumference would occur, how much change in circumference would occur if the material yielded. Basically, there is a thin pressure vessel, and it is you have to because of sorry because of the internal pressure, there is change in the length and circumference. There is a in you have and because there is a change in circumference, and the thing is uh, like the material starts to yield at 250 MPa, and using the maximum shear stress criteria, we have to calculate that how much is the change in length and the circumference when the material starts yielding. So let's in let us denote the internal pressure as P. Okay, P is the internal pressure. Sigma theta is equal to PR by T. Sigma Z is equal to sigma theta by 2, which is PR by 2T, and sigma R is equal to 0. Now we have to use the maximum shear stress criterion. Maximum shear stress criteria. So here I would like to show you that like before this, see the situation is something like this. Let's say this is the z axis, this is your theta axis, and there is a pressure P acting. Okay, and sigma theta and sigma uh, z are the two stresses developed. Sigma theta is the stress in the longitudinal direction. Sigma theta mm, is uh, is like sigma radial is 0. So okay, maybe if I cut a plane, that will be easier to understand. Suppose I cut a plane like this and take a look on this. Like I cut out a, suppose a thin ring like this. So here in the z direction, like in this direction, in it's clear from this diagram only. So if you, yeah, let's cut out a thin ring like this, and which is acted upon, suppose you are looking at the ring from this direction. I want to draw a circle. Now this is the thin ring which I have cut. So if I cut it like this, there will be some F tangential force in this direction, and let's say the radius is r. So, and you have a pressure P acting. So you can write 2ft is the force in the vertically downward direction, is equal to the this pressure force on this projected plane, and let's say this ring has a width of b in this direction. B is the width. Basically, I'm trying to explain what is this sigma theta and sigma z, so that you will be able to appreciate this. 2r into b, this is the area of the projected plane, multiplied by p, pressure, like projected in the sense the projected area over which this pressure p is acting. So ft is equal to prb, right? You can also write, suppose I look at this much length, this this area which I just highlighted. Over this ft force is equal to the sigma theta stress into b into t. This, if you equate, sigma theta bt is prb. So sigma theta is equal to pr by t. So this is sigma theta. That is the stress in this in the direction of this ft. Okay. Now what will be fz? Fz, what will be this sigma z? You can calculate sigma z like this. That also I'll just show. Sigma theta is crucial. Sigma z is PR by 2t. This I can show like f2 I have okay. I'll just think about this derivation. Like right now, I'm not getting it. So this sigma, I hope the sigma theta is clear. And the point which I wanted to make is if you look at this, let me cut a section. Let's say here. The point which I wanted to make is now you will have a certain stress throughout the circumference. This is, let's say, sigma z. And let's say you have a shear stress as well. And let me call the shear stress tau z theta. Now, if I take the moment about the point, this point, let's say O, the moment about z is 0. So, summation of moment about 0 is equal to 0. Or we can say that tau theta z should be equal to 0 because apart from this shear stress, you don't have any other force generating a moment. So the we can conclude that this theta z is the principal axis. That is the axis on which the shear stress is 0. So from here we can calculate, we can conclude that theta z is the principal axis. Why it is the principal axis? Because the shear stress is 0. Now we will use the maximum shear stress criteria. Okay. Maximum shear stress criteria. From the Mohr circle concept, we know that, let's say this is major principal stress, this is minor principal stress, this is shear stress. So maximum shear stress tau max is major principal stress minus minor principal stress by 2. Now let's use this concept here. That is sigma 1 minus sigma 2 by 2 is equal to the uh, like you are using the Tresca criteria, which is equal to y by 2, y being the yield stress of the material. So let me write it with the sigma max minus sigma min is equal to y. Now we know sigma max is equal to this theta, sigma min is equal to this sigma z. So sigma max is equal to sigma theta, sigma min is equal to sigma z. Minor principal stress. Why is the minor principal stress? sigma minimum is equal to this. This is not a principal instrument. Okay, this is they are considering the okay sigma. We have the sigma theta, we have sigma z, we have sigma r. This is this. Okay, this is sigma theta. Okay, here we are considering the what do I finally need to calculate? Finally, you need to calculate these two quantities. So sigma minimum is nothing but sigma r. Okay. So from this condition, we can tell sigma theta minus 0 is y. Y is nothing but the yield stress of the material, which is 250 MPa. So sigma theta is 250 MPa. Now sigma z is sigma theta by 2, which is 125 MPa, and sigma r is given as 0. Now epsilon theta, that is strain in the theta direction, will be sigma theta by E minus nu sigma r by E minus nu sigma z by E. So see, whatever I explained here, theta, z, and r, here I should write r as well. These are the principal axis, and this is the 3D state of stress. And for 3D state of stress, we had learned this concept, right? You have, so here basically what is happening, this is sigma theta, then you have the axis passing through like this. So this is sigma r and this is sigma z, right? This is a 3D state of stress. And like for simplification, what I was explaining through this, theta, z, and you have a theta to z, r, r. I should theta to z, r. Let's draw r like this. This is your r axis. Okay. Now what I was doing, I want to calculate epsilon theta and epsilon z. Now epsilon theta, sigma theta by E minus nu sigma r by E minus sigma z by E. Now let's take 1 by E common. So sigma theta minus nu sigma r. Okay. E is given in the question to be. Is E given? E is not given. So let's take E to be 200 GPa. So E is 200 into 10 to the power 3 MPa. Sigma theta is 250 MPa. Is Poisson ratio given? Poisson's ratio is also not given. It should be given. Let's take nu to be equal to zero point 0.3. Okay. Sigma r is equal to sigma r is 0 and sigma z is 125 MPa. So just substitute it. If you solve this, you will get the number to be equal to will be 1062 into 10 to the power minus 6, or okay. Now let's calculate epsilon z, which will be 1 by E then sigma z minus nu sigma theta minus nu sigma r. So 1 by 200 into 10 to the power 3. Sigma z is 125. Sigma r is 0 minus zero point 0.3 into sigma theta is 250. This you will get to be, let's calculate the number. So 0.25 into 10 to the power minus 3. So this is, let's write into as 10 to the power minus 3. Now I have to calculate the change in the length. So change in length that is related to the z direction or epsilon z. So percentage change in length is nothing but delta L by L into 100. Delta L by L is nothing but epsilon z into 100. So 0.25 into 10 to the power minus 3 into 100 is 0.025%. And change in circumference means which is related to the theta axis. Theta is uh, like which is related to the circumferential direction. So change in circumference is equal to, it will be simply be epsilon theta into 100, which is 1.062 into 10 to the power minus 3 into 100, which is 0.1062%. Okay. Now this exercise was done to locate the principal axis, because without locating the principal axis you cannot write down uh, the maximum principal stress. Sorry, you cannot write down the maximum shear stress. This is the maximum shear stress, and that is equal to the maximum shear stress when the material is under uniaxial tension. Like this is what the maximum shear stress criteria tells, that the stresses in uh, a 3D state of in a 3D state of stress, the maximum shear stress is equal to the maximum shear stress generated in a body when it is under uniaxial tension. Here Y is equal to the yield stress of the material. And here we have a 3D state of stress, sigma r, sigma z, sigma theta. From here you calculate the, you apply the maximum shear stress criteria and calculate sigma theta, sigma z, and sigma r. Sigma r is given to be 0. So you calculate sigma r, sigma z, sigma theta, sigma z, and sigma r. You develop a relationship like numerical values for them. Calculate the strain in the theta direction and in the z direction. Z direction is related to the length of the cylinder, which will give uh, a measure of uh, the change in the length because of the yielding of the material, and theta direction, which is related to the circumferential direction. So epsilon theta is the change in the circumference length by the total circumference length, and just it is a measure of the change in the percentage change in circumference provided that the material has yielded. So this is the third question. Okay, let's go for one more question. So you have a setup like this. You have a like inner cylinder, diameter 20 mm, and it is made up of steel, and over that, like you have an outer cylinder, diameter is 50 mm, and it is made up of basically you have a shell over it. It is made up of aluminium, right? And this length is 200 mm, and it is given that the Young's modulus of aluminium EA is 70 GPa. The coefficient of thermal expansion is 23.6 into 10 to the power minus 6 per degree Celsius. This aluminium shell, it is fully bonded to a steel core. So an aluminium shell is fully bonded to a steel core, and the assembly is unstressed at a temperature of 20 degrees Celsius. And the assembly is unstressed at an temperature of 20 degrees Celsius. Considering only axial deformations, you have to determine the stress in the aluminium when the temperature reaches 180 degrees Celsius. Considering only axial deformation, determine the stress in the aluminium. You have to determine the stress in the aluminium when the temperature reaches 180 degrees Celsius. For steel, Young's modulus is 200 GPa, and coefficient of thermal expansion is 11.7 into 10 to the power minus 6 per degree Celsius. So I'll give you a few minutes time. think about this question. And in the meantime, quickly, we'll take a break of 5 minutes and then we'll come back and discuss this question. So let's meet in 5 minutes. Okay, welcome back. Let's resume this discussion. So, basically you have a steel core, and over that you have a aluminum shell, and it is bonded, fully bonded with it. And this entire assembly is subjected to a change in temperature. Initially it was at 20 degrees Celsius, and the temperature was increased to 180 degrees Celsius. Because of this increase in temperature, and you have to calculate the stress in the aluminum. Okay. Now, as you can see, the since it is fully bonded, the steel and aluminum will not lose contact. But we know that because of change in temperature, the in what is the uh, increase in length? It is like L alpha delta T. That is the increase in the length. Now, the alpha of the two materials are different. Alpha of aluminum is more, that is, it will undergo more, it will expand because of increase in temperature, it will expand more than that of the steel. So, more expansion in aluminum, less expansion in, there will be like the tendency, the the extension will be more in the tendency of expansion will be more in aluminum than that of steel. So but both are bonded, so aluminum will have to expand less, steel will have to expand more. Because steel has to expand more, there will be tensile stresses. Aluminum will expand less, so there will be compressive stresses in the aluminum. Now, let's like formally put this up in a discussion, and let's calculate the magnitude of stress in the aluminum because of the change in temperature. Now, the area of steel is pi by 4 into 20 square, which is 314.159 mm square. Now, this area of aluminium is pi by 4 into 50 square minus 20 square. This is a trivial calculation. Now, let PS be the axial force which is carried by the steel core, and PA be the axial force which is carried by the aluminium uh, shell. Now, the total force acting on the system, P, there is no external force acting on the system. So, the force carried by steel is equal to that of the aluminium. Okay. If let P be the total axial force, okay, PA be the axial force carried by the aluminium shell, PS be the axial force carried by steel core. So external force is equal to PA plus PS, but external force is 0. So PA is equal to minus of PS. Right. Now, since this steel core and the aluminum shell will act as an assembly, it can't lose the bond. The deformation will be equal. So let delta be the deformation. Because of, let me call delta A to be the deformation in aluminum, and delta S is the deformation in the steel core. Now in the aluminium, the force is Pa. We know that because of an axial force, the deformation is PL by AE. So PAL by E of aluminium and area of aluminium. And because of increase in temperature, it is L alpha A delta T. Okay. And in steel, it is PSL by E of steel, area of steel, plus L alpha of steel delta T. Now, these deformations have to be equal because it can't lose bond. So, PAL by EA plus L alpha A delta T is equal to PSL by ESAS by L alpha S delta T. Now L is common on both the sides. We can remove them. And we can rearrange the equation, write it as PA by EA by AA minus PS by ES into AS is equal to alpha S minus alpha A delta T. Now PA is equal to minus of PS. Let's use the thing here. PA, let me take common. EAAA and minus of PS is again PA and PF taken common. So plus by ES by AS. And let this side be alpha S minus alpha A delta T. Now let's plug in the numbers. PA is equal to 1 by what is Young's modulus of aluminium? 70 GPa. So 70 into 10 to the power 3. And what is the area of aluminium? We just calculate area of aluminium to be this number. So 1.649 into 10 to the power, sorry, this is minus 3. 70 GPa. So here I am working in the units of Newton per meter square. So that is why I have a 10 to the power minus 3 conversion unit. Okay. So here I am working in the units of Newton per meter square. Okay. Plus 1 by of steel. EA is 200 GPa. Yeah, 200 into 10 to the power 9. 10 to the power 9 is gigapascal. So 10 to the power 9 into 314.159. This is in mm square. So you have a 10 to the power minus 6 since I'm converting it into meter square. This is equal to alpha S minus alpha A into delta T. Now alpha S is 11.7. Alpha is A is 23.9. So alpha S is 11.7. This is 23.6 into 10 to the power 6. We have that. So let's take that common. And temperature increases. Final temperature is 180 degrees Celsius. Initial temperature is 20 degrees Celsius. So if you solve this, you will get Pa to be equal to minus 77.4 kilonewton. So the stress in aluminium will be the load in aluminium by the area of aluminium, which is minus 46.9 MPa. And we can see in aluminium a negative stress that a compress or a compressive stress has been developed. This, like what I was discussing right before starting the question. So this negative sign shows a compressive stress has developed in the aluminium. Okay, next, let's quickly do one more question. Okay, this question, something related to temperature. So this will be your question number 5. So you have a system like this. This is A, B, and C. Diameter of the cylinder is 30 mm, and this is 50 mm diameter. This length is 250. This length is 300. So the question reads that a rod consisting of two cylindrical portions AB and BC is restrained at both ends. So it is restrained at both ends. Portion AB, it is made up of steel. So this is AB is made up of steel, and Young's modulus is 200 GPa, and alpha S is equal to 11.7 into 10 to the power minus 6 per degree Celsius. And the portion BC is made up of brass. Young's modulus of brass is 105 GPa. Alpha B is 20.9 into 10 to the power minus 6 per degree Celsius. Knowing that the rod is initially unstressed, you have to determine the compressive force introduced in ABC when there is a temperature rise of 50 degrees Celsius. So if there is a temperature rise of 50 degrees Celsius, the arrangement will try to expand. So because as the temperature, the setup will try to expand, compressive stresses will be developed in the system ABC. You have to calculate that compressive force. So knowing that the rod is initially unstressed, determine the compressive force induced in ABC when there is a temperature rise, when there is a temperature rise of 50 degrees Celsius. So so you have a system like that, and it is subjected to compressive. Let the compressive force be F, right? This is A, B, C, and let me call the force P. This length is 250 mm, this length is 300 mm. Now, area of AB is pi by 4 into 30 square, which is 706.86 mm square, and area of BC is pi by 4 into 50 square, which is 1963.5 mm square. Now, there is a free thermal uh, because of the change in temperature. This setup will try to increase in length. So because of the change in temperature, let the deformation be delta t. It will be alpha s LAB delta T. This is for the cylinder AB, and for the cylinder BC, it will be alpha B because it is made up of bronze into LBC into delta T. Now, alpha S is 11.7 into 10 to the power minus 6. Length of AB is 250 and delta T is 50 degree Celsius, and alpha B is 20.9 into 10 to the power minus 6 into length of BC is 300 into delta T is 50 degrees Celsius, the rise in temperature. So this delta T comes out to be 0.45975 mm. Now, because of this axial force P, there will be uh, certain compression. Let's calculate that compression. So delta P. So because of this delta T, there is expansion because there is a rise in temperature, and because of the compressive force, there is shortening. Okay. Now delta P will be PLAB by ES into area of AB plus PL length of BC by, this is made up of bronze, and area of BC. Now P, we are substituting working in the units of Newton meter. So length is 250 mm, so 0.25 meter. Area of Young's modulus of steel is 200 GPa, so into 10 to the power 9. And the area of cross section of AB is 706.86 into 10 to the power minus 6. P into length of BC is 300 mm, so 0.3 meter. Young's modulus is 105 into 10 to the power 9. Young's modulus of bronze into area of BC is 1963.5 into 10 to the power minus 6. Uh, so basically conversion from mm square into meter square, that is why. So if you solve this, you will get 3.22 into 10 to the power minus 9 p. Now, here is the catch. Since this system, it is fixed from both the sides, it can't move. So this elongation due to the temperature, the expansion should be equal to the shortening due to the load. So delta T is equal to delta P. So 3.22 into 10 to the power minus 9 P is equal to 0.45975 mm. So if you solve this, you will get the value of P to be 142.6 kilonewton. So this is, you use the the boundary conditions of the system that it can't move to calculate the axial force because of the change in temperature. So let's quickly do one more question. So let's do this question. You have a system like this. This is C, this is E, this is D, A. This length is 0.9 meter. Hang on for a second. Yeah. This length is 0.3 meter. This is 0.3 meter, 0.45 meter. The question reads that there is a rigid bar CDE. It is attached to a pin support at E and it rests on a 30 mm brass cylinder BD as shown in this figure. Okay, a 22 mm diameter steel rod AC passes through a hole in the bar and it is secured by a nut that is snugly fitted when the temperature of the entire assembly. So you basically have a nut here, and this is a brass cylinder, and this is a pin type of connection. The temperature of the brass cylinder is then raised to 50 degrees Celsius while the steel rod remains at 20 degrees Celsius. Assuming that no stresses were present before the temperature change, we have to determine the stress in the cylinder. So, rigid bar CDE is pin supported at E and it rests on a 30 diameter brass cylinder. So, BD is a brass cylinder with 30 dia. A 22 diameter steel rod AC, 22 dia steel rod AC passes through a hole in the bar, passes through a hole in the bar and is secured by a nut that is snugly fitted and is secured by a nut that is snugly fitted. Okay. When the temperature of the entire assembly is 20 degrees Celsius. When the temperature of assembly is 20 degrees Celsius. Now, the temperature of the brass cylinder is then raised to 50 degrees Celsius. Temperature of brass cylinder is increased to 50 degrees Celsius while the steel rod remains at 20 degrees Celsius. While the steel rod remains at 20 degrees Celsius. Assume that no stresses were present before the temperature change. You have to determine the stress in the cylinder. Determine the stress in the cylinder. It is mentioned that for brass, Young's modulus is 105 GPa and alpha is equal to 20.9 into 10 to the power minus 6 per degree Celsius. For steel, E is equal to 200 GPa and alpha is equal to 11.7 into 10 to the power 6 per degree Celsius. So first, we'll draw the free body diagram of this system. So C, D, E. E is spin supported. So you have the reaction EX and EY. On the cylinder B, it is just simply supported. So you have the reaction R. Let it be with the cylinder. So there will be a reaction RB. Okay. This is 0.45 meter and this is zero point 0.3 meter. And you have a rod here and the reaction is Ra. This is A. Okay. Now, if I take the moment about point B, then I can develop a reaction between Ra and Rb. This is the first thing which I do. So, moment about E is equal to 0. So, Ra into 0.75 minus Rb into zero point 0.3. Like at this stage, you should be able to write this very comfortably. You are taking the moment about point E and I am writing anti-clockwise moment to be positive. So Ra is 0.4 Rb. Okay. Now there is a temperature rise of from 20 degrees Celsius, the temperature is increased to 50 degrees Celsius. So there is a temperature rise of 30 degrees Celsius of the brass cylinder. And because of this, the length of the brass cylinder increases. So delta T of the brass cylinder increase in length will be L into alpha into delta T. Now length of the cylinder, brass cylinder is 300 mm. So zero point 0.3 meters. Alpha of the brass is given here 20.9 into 10 to the power minus 6 per degree Celsius and increase in temperature is 30 degree Celsius. So this comes out to be 188.1 into 10 to the power minus 6. This is the increase in the length of the brass cylinder. Now, if there is an increase in the length of the brass cylinder, so let me first draw the diagram. when my support at B is removed. So the system will look, let me draw this. So at A, it is supported like this. Let's say at B, the support has been removed, and because of the increase in temperature, the length has increased delta D, and it is positive. Okay, and it is been supported at E. This is D. This is C. Now, what will happen? Now let's apply the support reaction. Let's at B. RB is in the vertically upward reaction, and let's assume because of these support reactions, the bar rotates like this. Let's assume this has happened. Okay, this is pinned, so this will not move. And let's assume that this bar has also stretched like this. This is RA. Okay, and then this will be delta C. This is point C. Let me assume this is D. Now this, you can develop a relationship between delta C and delta D, because let the try this because delta C and delta D are related from similarity of this triangle and this triangle. Okay, I'll just remove this, otherwise it will become crowded. So I can write that delta D divided by this length, that is zero point 0.3, is equal to delta C divided by this length, which is 0.75 meter. So delta D and delta C are related. So delta D is equal to zero point 0.4 times delta C. So this diagram is because of when the support at B is removed. This is the reaction at B is applied, and then let's just s- like superimpose this, and this is what the final condition should some be. Something should be like this, like this line is for point E does not move from that line, so E remains as it is. B also remains on this line. It can't move actually because it is supported, and this can undergo an extension. AB can AC can undergo extension like this. This is delta C, and this is the final position. So, so basically, I am doing a superposition of the thermal and the restraint force diagram. This is because of the thermal and this is for the restraint force deformation. So basically, here we are doing a superposition of thermal force diagram, thermal and restraint force deformation. So, like from the first diagram, I'm showing that when the support at B is removed, okay, you're removing the support, there is a rise in temperature, and which causes the temperature rises of the cylinder causes the point B to move downward through delta T, and we calculated delta T to be 188.1 into 10 to the power 6, and this should be in meter. Okay, and then the reaction at RB must cause a deflection. Let's say this deflection is because of this reaction, there will be movement delta 1, which should be equal to delta T, so that the final deflection at B should be 0. So we develop the relationship like so. I'll write down all the relationship which we have developed. Delta D is zero point 0.4 delta C. This we had developed here. Now delta 1 will be delta at D plus now I can calculate delta C. First, let's calculate delta C. I'll just finish the question and wind up the class. Delta C, that is deflection at in the member AC, will be because of the axial force RA. So RAL by AE. Let RA will be like RA, be written as RA. The length of the member AC is zero point 0.9 meter. See, here it is 0.9 meter. 0.9 meter. And area AC, the member AC is 22 mm diameter and it is made up of steel. So diameter is 22. So pi by 4 into 20. I want the answer to be in. So 22 divided by 1000 will give me in meters, and the square of that into E, it is made up of steel. So Young's modulus of steel is 200 GPa. So 200 into 10 to the power 9. Okay. So this comes out to be 11.84 into 10 to the power minus 9 Ra. Now delta D is zero point 0.4 times delta C. You just calculated delta C. So this comes out to be 4.74 into 10 to the power minus 9 Ra. Now this deflection is in the upward direction. Delta D is also in the upward direction. So deflection at B deflection at B will be RBL by AE. Now RB length of the brass cylinder is zero point 0.3 meters. So RB into zero point 0.3. Diameter of the brass cylinder is 300 mm. So pi by 4 into zero point 0.3. Brass cylinder, diameter of the brass cylinder is 30 mm. Sorry, not 300 mm. 30 mm. So 0.03. And it is made up of brass. So Young's modulus is 105 GPa. 105 into 10 to the power 9. If you solve this, you will get this to be 4.04 into 10 to the power minus 9 RB, which is again in the upward direction. So, this entire deflection at 1 will be deflection at, like, because of the deflection in the member AC, there is deflection at D. So delta D plus delta B, which is because of the force in the member, force in the bar BD. So because of delta C, you have delta D, and because of RB, you have a deflection in the upward direction. So the total deflection will be the summation of the two deflections, which comes out to be 4.74 into 10 to the power minus 9 RA plus 4.04 into 10 to the power minus 9 RB. Now we know RA and RB are related to each other. So RA is zero point 0.4 times RB. So substitute it here. 4.74 into 10 to the power minus 9. RA is equal to 4.4 times RB plus 4.04 into 10 to the power minus 9 RB. So this comes out to be 5.94 into 10 to the power minus 9 RB. Now we know that the deflection due to the increase in temperature is equal to this delta 1. So because of temperature, you have 188.1 into 10 to the power minus 6 meters, and this deflection is 5.94 into 10 to the power minus 9 RB. So from here you can calculate RB to be 31.7 kilonewton. Now once you know RB, you can find out the stress in the cylinder BD. Stress in the cylinder BD. Stress in BD will be RB divided by the area A of the cylinder. So 31.7 kilo Newton. So into 10 to the power 3, this is in Newton. And area, suppose I want in mm square. So pi by 4 into 30. 30 mm, 30 square. This is in mm square. So the answer is 44.8 Newton per mm square or MPa. So this is how I calculate the stress in the bar BD. So any doubts in this question or in the previous question, previous questions which I have covered? I'll be uploading these hand lights, like the notes as well. You can have a look at them. If you have any doubts, you can always drop down an email. My email ID is Sukanya K21, SUKANYA K21 at the rate iitk.ac.in. So, if you have any doubts, please drop an email. If you find something incorrect in the solution, any calculation, do drop an email. So, do you have any doubts now? Any thing related to these questions, or in the video lectures, or in the assignments whose answers have already been given, the previous assignments? Okay, I have already crossed my scheduled time, so uh, I think so I'll close the lecture today. And if there are any doubts, you can always drop an email. So, okay. 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 I'll close the session. Thank you so much for attending the session.